ladies and gentlemen, welcome to another tutorial from me, the code.Pylet. It's funny, I say ladies and gentlemen, but looking through my channel's analytics, it shows that only 4% of the people that visit this channel are actually female. It's weird, isn't it? What's going on? Anyway, I'm rambling. In a previous video I did called Scrolling Background with Player, I briefly touched upon something called the stage. So in this episode, we're going to expand on that subject by adding layers to give the appearance of distance and manage objects so they move about on the display surface. Let's have a quick look at the finished product. The block in the middle of the display, which I've called the fish, is controlled by the mouse. The grid is to show that the fish is moving about on the stage. Normally when you follow these tutorials, the code is structured inside a template like this. Variable declaration followed by the main loop. Sometimes there's a class thrown in too. We're going to be doing things a little bit different in this video. We're going to create a separate file called a module, which will allow us to assemble the code for the stage and import it into our test script. And yes, the test script and stage module both contain classes. To start with, I'm going to take you through the stage module. But before we do, let's have a look at the structure of the stage module and what each bit does. There are two classes in the stage module, Viewport and Manager. The viewport is a movable area the size of the display surface that checks an object's position and dimensions to determine if it's inside it or not. The manager allows us to add objects to a multi-layered stage and manipulate them using the object's own methods. You can also set an object as a focal point so the viewport tracks it as it moves. So, before you all die of boredom, I better get explaining. The viewport class in our stage module makes use of Pygame's getSurface function to create an instance of the display surface. This is where we have to include the line import Pygame. Without import Pygame, we wouldn't have access to any of Pygame's functions. As you can see, viewport is the first class in the module and contains 4 methods and an initialization function. The 4 methods are setLocation, objectVisible, center on X, and center on Y. This is the viewport's initialization function, and it accepts just one parameter, a display surface object. If no surface object is supplied, then the surface variable defaults to none. The if statement here checks whether the surface parameter is false, but bear in mind that a none value is also false. If it is false, then ask Pygame for an instance of the display surface by calling the getSurface function. We also need to create our own instance of the display surface object to use later when we're either drawing or blitting. This next line of code calls the getRect function associated with our instance of the display surface object. It returns a rect object which contains all the information we need to know about the dimensions of the display surface, such as the size and center values. Here, we're now splitting up the rect object's size attribute containing the width and height values into separate width and height variables. This is so we can access these values through meaningful names rather than referencing them as elements in a list. This next line does the same, but instead splits the rect object's center attribute into its component half width and half height values. The last line in the initialization function sets the default location of the viewport on the stage. Here the X value is 0 and the Y value is 0. This places the viewport at the top left of the stage like this. SetLocation is fairly self-explanatory. It just places the top left corner of the viewport at the X and Y coordinates supplied in the parameters. What it doesn't do is check whether the coordinates take the viewport outside of the stage. We won't be using this function in this video, so we don't really need to think about it right now. The objectVisible function here takes one parameter, an object. An object is basically an object that has X, Y, width and height attributes. The object can also have the following methods: move, draw and extension, but these are optional and don't have to be defined. We'll be covering the methods in a bit more detail later on. For this next bit, let's assume that the object in the parameter has the correct X, Y, width and height attributes. We know that the viewport and the object both have X and Y attributes, and they refer to a location on the stage. The if statement here uses these attributes to determine if the object is outside of the viewport by testing 4 conditions. If any of the 4 conditions are true, then the function returns false. The object is outside of the viewport. The first condition asks if the object's X location is less than the viewport's X location minus the object's width. We can look at this diagram to see this in action. Okay, so let's add some labels. This is where the viewport's X location is. This is where the viewport's X location minus the object's width is. And this is where the X location of the object is. In this state, you can clearly see that the X location of the object is less than the viewport's X location minus the object's width, which means the condition is true and the objectVisible function returns false. In this state, the object's X location is greater than the viewport's X location minus the object's width, so the condition is false. This means we can move on to the next condition. The next condition asks if the object's X location is greater than the viewport's X location plus its width. In this state, you can clearly see the condition is true because the object's X location is greater than that of the viewport's X location plus its width. So in this case, the objectVisible function will return false. Now, the diagram shows that the object's X location is less than the viewport's X location plus its width, so the condition is false. And the other two conditions focus on testing the viewport and object's Y location in exactly the same way, so I won't waste your time demonstrating them here. Let's go back to the code. So to summarize this function, if the object is outside of the viewport, it returns false, else it returns true. Let's move on to the next functions, center on X and center on Y. These functions center the viewport over their parameter by deducting half of the viewport's width or half of the viewport's height from it. That is of course dependent on which function you call. It's a fairly straightforward procedure, but for those that don't understand, we can have a look at this diagram. The green X and Y you can see here represents each of the function's parameters. In the center on X function, we have this equation, which is basically saying make the viewport's X location the same as the X location from the parameter minus half the width of the viewport. The result is this. The viewport is centralized to the X coordinate from the parameter. The same is also true for center on Y. It centralizes the viewport over the Y parameter. If we call both functions one after the other, then the viewport is centralized horizontally and vertically. We use this function later to centralize the viewport over an object in focus. So, that's the viewport class done. Let's move on to the next one, the manager. Just to recap, the manager is responsible for keeping track of all the objects on the stage and calling their various methods. It can also focus an object so that the viewport tracks it as it moves about. The initialization function requires three parameters, the number of layers and the width and height. Theoretically, you can have as many layers on the stage as you like, but the more you have, the more CPU processing is required. The stage's width and height values are only limited by Python's ability to compute large numbers. But unless you're making a space game which allows huge areas with very few objects in, you're going to have the same problem as with the layers. Filling a large stage with objects is going to be heavy on the CPU. On a side note, the stage's layers are ordered so that layer 0 is the furthest back and subsequent layers are stacked towards the foreground. Moving forward then, the first line inside the initialization function stores the width and height parameters in the manager object. We'll need these values later to restrict the viewport and also pass them to the objects on the stage so they can manage their own boundaries. Next, we're creating a new viewport object and storing the number of layers. There really isn't much more to say on that, so we'll move on. This next line is important because it creates a container for the objects on the stage in the form of a multi-dimensional list called objects. The first dimension of the objects list represents the layers, and each layer has an empty list attached so we can append the stage's objects to it. This diagram is a graphical representation of it. The squares represent the stage's layers, and as you can see in this example, there are 3 of them. The circles are the objects assigned to the 3 layers. On layer 0, there are 4 objects, layer 1 has 6 objects, and layer 2 has 1. If you wanted to access an object directly, you can code something like this. Here, creating an instance called myObject from object 5 on layer 0. The last line in the initialization function sets the focus object for the viewport to follow and centralize to. Here, the default value is none, which means the viewport will remain static to its own x and y coordinates. These next 2 functions simply set and remove the focus object for the viewport to centralize and follow. Really, you could just set the focus without calling the manager's focus on or off methods by assigning an object to the focus variable. But, in my opinion, this way seems a little neater and more meaningful. This next method allows us to add objects to a layer on the stage. The parameters are simple, the layer index and the object to add. On this next line, we see that we're appending the object to the end of the objects list using the layer parameter as an index. I mentioned before that each object on the stage can have 3 methods. move, draw, and extension, but they don't need to be defined if the object doesn't need them. For instance, a platform doesn't need to do anything other than be drawn to the stage, so only the draw function needs to be defined. These three lines determine if such methods exist. This is important because if you try to call a function that doesn't exist, it will break your program. So, rather than testing for the existence of a method each time, we simply determine once if the method exists and store that true or false value in a variable within the object itself. This last line returns the object passed in the parameters. Why? Because sometimes you may want to define an object within the parameter of the addObject method, but need an instance of it afterwards, like this. We're now at the last function in the manager class and also the last function in the module, so let's get this thing nailed. The do method cycles through each object on each of the layers, calculates the object's x and y location on the display surface, and calls the object's available methods. In the next line, the for loop generates a layer index. This is between 0 and the total number of layers created. We then use that index on this line to return a layer list containing all of its objects. As we cycle through the layer list, the variable called object becomes an instance of the current object. We next calculate the object's x and y location on the display surface. This is done now because the object's move and extension methods may need to know where it is on the display, especially if the object interacts with the mouse in some way. To get the object's position on the display surface, we simply deduct the viewport's location from the objects. This next line asks if the object has a move method. This is done by determining if the value of movable is true or false. If the object does have a move method, then we call it and pass its x and y location on the display surface and also the stage itself as the parameters. It's important to note that every object's methods require the same three parameters. The reason we pass the stage manager as a parameter to the object is because it may need access to the layers for collision purposes, determine the stage's boundaries, or get an instance of the display surface object from the viewport. One of the main features of the stage is to focus the viewport on an object, and in this next block of code we'll do just that. The focus variable shown in these two if statements will contain either of two values, none or an instance of an object on the stage. If the value of focus is an object, then we can test the current object in the loop and determine if it matches that of the instance. If it does, then we centralize the viewport to it. To centralize the viewport to the object, we call the viewport's center on x and center on y methods, but only if the object's position is greater than half the viewport's width and height from the edge of the stage's boundaries. Why don't we have a look at a demo for a better idea of what all this means? Here, the viewport is already focused on the object controlled by the mouse in the center of the stage. When the object moves, the viewport tracks it using the center on x and center on y methods. If the object crosses the green line, then the viewport no longer centralizes on that axis. Here, as the object moves to the top of the stage and crosses the green line, the viewport no longer centralizes on the object's y-axis, but continues to centralize on the x-axis. We see the opposite effect here, when the object moves to the left-hand side of the stage. The viewport stops centralizing on the object's x-axis. We know the purpose of the green line, which is made up of half the width and height of the viewport from the edge of the stage, is to stop the viewport centralizing to the object, but why do we need it? It's because without it, the viewport would leave the stage and nothing would be drawn or blitted to the primary display surface. And back to the code. Let's focus on this condition block, which relates to the object's x-axis. The first if is asking if the object's x position on the stage is less than or equal to half the value of the viewport's width. In other words, is the object too close to the left-hand side of the stage? If it is, then we set the viewport's x location to 0, effectively stopping it going outside of the stage's boundaries. This next part of the if statement is asking if the object's x location is greater than the value of the stage's width minus half the width of the viewport. In other words, is the object too close to the right-hand side of the stage? If it is, then set the value of the viewport's x position to the value of the stage's width minus the full width of the viewport, preventing the viewport leaving the stage. If none of the above conditions are true, then it's safe to center the viewport on the object's x-axis. This next if block does exactly the same, but for the y coordinate, so we'll move on. The last part of the do function determines if the object has a draw method. If it does, then we test again to determine if the object is inside the viewport. If it is, then we call the object's draw method, passing the x, y, and stage object as its parameters. Well, that's the end of the module. It actually took quite a lot longer than I expected, but yeah, I should imagine there's a few skeletons sat at desks right now. Oh, hang on a minute. You may be wondering where we call the object's extension method in the do function. To be honest, we're not going to bother calling it because it's not in the test script. If you want to use it, then place it just above line 57. Right, let's move on to the test script. So, before we start with the coding, head down into the description and follow the link to my Google Drive. From there, you'll be able to download the template. The template will help speed up this tutorial by having everything we've already covered typed up ready for us. If there's something you don't understand, then go back through my videos or leave a comment and I'll help you as best as I can. I'm a nice guy. Because the stage module is in a separate file, we need to import it. So we'll just pop this line in here and make it obvious that it's something we've done by giving it some space. So let's now scroll down in the template so we're just under the colour definitions. This is where we're going to construct the objects to go on our stage. The first is the block, which is a static white rectangle. Its purpose is to allow us to see the viewport as it moves about the stage by creating a grid pattern. The initialization function of the block class accepts three parameters: the x and y coordinate and the size. The size is a tuple containing two elements, the width of the block and the height. The next line creates a copy of the starting coordinates from the x and y parameter, because if you remember, all objects on the stage have to have four attributes: x, y, width and height. We'll add the width and height values now by splitting up the size tuple into separate variables. Here we're defining the block's draw method. This will be called by the stage manager and must include three parameters. You can give the variables in the parameters any name, but here I've used x, y and stage. If you don't include these three parameters and the draw object is called, then Python will invoke an exception at you. Bummer. Our block object will be coloured white, so we'll bring the white colour variable in globally. If you wanted to, for a wee bit of fun, you could create a colour variable in the block's initialization function and assign a tuple to it containing random red, green and blue values. Then you can use that to colour it. To draw the block to the stage, we'll be calling Pygame's rect function. If you need to know how to draw rectangles, then have a look at this video on shapes and coordinates. Let's have a look at a couple of the rect function's parameters. The first parameter requires a surface object, and here we're supplying an instance of our display surface from the stage's viewport object. The third parameter is a tuple made up of x, y, width and height. It's worth remembering that x and y have come from the stage manager and reference a point on the display surface and not a location on the stage. Well, that's the block created, so let's create the other stage object, which is called fish. It's called fish because I literally couldn't think of a better name for it. The initialization function of the fish object is virtually the same as the block object, but without the size parameter. This is because the fish has a set size of 25 pixels square. We'll need to make copies of the values too, which, as you can see, I've already started doing. The move method here, like the block's draw method, is also called by the stage manager and has to accept the same three parameters: x, y, and the stage. To move the fish, we need to calculate the distance from the mouse pointer to the fish on the display surface. Remember, we get the location of the fish on the display surface from the stage manager supplied through the move method's parameter. We then divide that distance by 50 and then add that value to the fish's location on the stage. So in this line, we're getting the mouse's position by calling the getPos function and splitting the result into two local variables, mx and my. We then create another local variable called xdist, which will contain the value of deducting the x location of the fish on the display surface from the x location of the mouse pointer and then divided by 50. The reason why we're dividing by 50 here is because we're adding xdist to the fish's x location on the stage. So if we didn't shrink that value by a considerable amount, the fish would move way too fast. It's worth mentioning here that the mouse's getPos function returns the location on the display surface and not the stage. The mouse isn't connected to the stage in any way. We next have to do the same distance calculation using the fish's and the mouse's y coordinate. Now we add the xdist to the fish's x location on the stage and ydist to the y location. That's the fish's move method complete. Now all that's left to do is the draw method, which you'll be pleased to know is virtually the same as the draw method for the block object. So we'll go up here and copy and paste it into the fish object. Then we'll change the last parameter in the rect function so that the rectangle is drawn as a solid block of colour and not as a line. Well, that's both stage objects done, so let's move on to the setup part of the script. Seeing as we've just spent 15 minutes talking about the stage object, we better include it in our script. This line defines an instance of the stage manager with a width and height 4 times that of the display surface. We're also just going to use one layer. cFactor stands for common factor and is assigned the value 64. 64 is one of 14 common factors between the width and height of the stage. The block size is based on the stage being divided up into a 64 by 64 block grid, which leaves us with a block size of 80 by 45 pixels. Now we have the block size calculated, we then need to start adding them to the stage. We'll do that with a for loop. The range of the for loop is based on a grid of blocks with a dimension 64 by 64. This gives a total range of 4096. The variable a represents the loop's index and will have a starting value of 0 and an ending value of 4095. We'll be using that value to calculate the position of each block on the stage. Let's have a look at a demonstration to understand how the block's x and y values can be got from a sequential number. The x value is calculated using the modulus operator, which returns the remainder after dividing a by the common factor and multiplying the result by the block's width, 80. The y is similar, but is calculated by dividing a by the common factor, ignoring the remainder, and multiplying the result by the block's height, 45. So as a increases, the blocks are stacked in a nice grid. You could achieve the same effect using 2 for loops, one for x and one for y, but I personally prefer just one loop. That's enough of that rubbish, back to the code. We'll start by calling the stage's addObject method and passing an instance of a block to it. The block's parameters are x, y and size, which we've just discussed in the previous demonstration. So pardon me while I speed this bit up, as it should make perfect sense now. Now we have to add the fish to the stage manager and place it in the centre of the stage. If you remember, the add object returns the same object passed to it in the parameters, which is really useful as we can grab our own instance of the fish to use however we like. In this next line, we do just that. We call the focusOn function and pass our fish object to it. Now the stage's viewport will centralize to the fish object as it moves about using the mouse. All that's left to do now is add the stage to the main loop and call its do function. Well, that's it folks, all the coding done. Let's head over to the command prompt and run this sucker. Yes! Through the power of video editing, it worked. No bugs. Don't forget, all my scripts are available from my Google Drive. Download, tinker with it. You can even plagiarize them for your college work if you wanted to. Actually, don't do that. I hope you've enjoyed watching this, and I'm sorry it was a long one. 23 minutes for a YouTube video is like death. But you're still here. Well, some of you. And hopefully I'll see you for the next one. In the meantime, if you have any questions, then please go into the comments. I try to help as many people as I can. Bye for now.